on this, anybody has a question? Like maybe one question I can take right now, and then I start the session. Okay, if not, then I will. I think I'll stop my video feed because makes it faster. I'll open it again later. So otherwise, the video will take the bandwidth. So I don't want that to happen. So right. So the topic that I am going to discuss. So my expertise is astronomy and radiation in astronomy. So I work on a lot of things like how radiation propagates through the gas and how it propagates through the gas in early galaxies. So that is my expertise. But as the saying goes, it is all about photons. So the fundamental aspects of the problem that I work on, or anybody else works on, whether he is in the quantum mechanics or in material science, but if you are talking about the propagation of light, then the fundamental aspects of the problem, that is fundamental physics, do not change. So the ideas that I will be presenting to you are at a very basic level that I have been thinking about for quite some time during various teaching and other activities that I have been involved in, and also from my research. So this is a kind of a realizations I have had, and so again, it will be really beneficial for somebody who is beginning. And if you are already teaching at various levels, as I see many of you are much more experienced, so for them, I hope it will be a very layerly talk, and so again, worthy of discussion at any point. You may come in. How do you like it, or like whatever I am presenting in this session. So briefly about myself. So to add a point here that if in case somebody is missing on voice or so, or my voice is not clearly audible, then please interject briefly so that I know. Otherwise, I'll be keep on speaking, and there has to be some input from the other end that there is some breakage that has happened. Okay, so let's continue. So this is just so that you know me. So I am an assistant professor here at the IIT Bhilai, and as I mentioned, my expertise is astrophysics, cosmology, and fluid dynamics, and hydrodynamic simulations, radiation hydrodynamic simulations, and radiative transfer in early galaxies and in the local universe. The H2 regions, H2 regions are basically the ionized hydrogen regions. The ionized hydrogen that is around the stars, those are dying, and in the stellar nurseries, and there how the photons actually go and ionize the system. So that is the key research uh, uh, focus that I have. So I did my master's from the Institute of Technology, Roorkee, and PhD from the Raman Research Institute in Bangalore. So this institute, which was created by Sir C.V. Raman, and then I moved on to UK to the Institute of Computational Cosmology in Durham University, where I was a postdoctoral fellow for 4 years. And later on, I took up a position in the International Centre for Radio Astronomy Research in Australia as an Astro 3D fellow before joining here as an assistant professor. So, okay, so let's do this on side, and now let's get on with the topic at hand. So I thought where to begin this talk. So I am speaking about radiative transfer, the propagation of light or so. So light again is the main theme of this conference on photonics. So where should one begin? And since ancient times, so we have been fascinated about light. So even so in front of you on your screen you see, as you all, not maybe all, at least people from this part of the country, eastern part, they would recognize, and maybe all of you, that this is the famous Konark temple, the sun temple, and this is an old temple, as you know. And then on the right you see, I don't know if someone can guess, that is in the Jaipur, that is a kind of a solar observatory that was built by I guess by King Jasim, if my knowledge is correct. So light has been fascinating us. It has been people have invested time and money and all things from ancient kingdoms, and not just there. I mean, even in the prehistoric times, at the beginning of the civilization, the light has been a key part. And in our country also, in the very recent times, the light should reach every part. So that is basically electricity they talk about. But you know how important that is for the our country, for our country to become educational hub, so that every kid in the even in the rural areas, they should be able to have uh, access to basic infrastructure and necessities. So people didn't have electricity up to a one point of time. But let's coming back uh, uh, to the topic. So light is one key aspect that has been all around us. We have been thinking about it, and later on in 20th century, it has led to the development of really key fundamental physics related to light, where people started thinking, okay, light is like waves, light is, then all optics was developed, and then later on that the light is like, okay, it behaves as particles, so which is the wave particle duality, and the quantum mechanics was developed. So it has been a subject that is uh, developed in the higher research, in the extremely high end research, as well as it is a basic necessity for almost all the living beings on earth, not just human. Okay. Right. So moving on, just forwards, as I already mentioned, that this is the optics uh, book that is written by Euclid way back. So when the first, I would say, first proper footing on which the study of light was brought on by this memoir, or writing these research books that, for example, was developed famously by Euclid, and later, uh, or maybe contemporarily at the same. The Ptolemy also had a book on optics. So this is in, I would say, Latin or Italian language that is written. This one, Firenze, you can see, and this is the optics book that was there. So just don't worry. So I'll be increasing the technicalities bit by bit. So just giving you the brief flavor. So this is the optics that we knew at the time of Euclid. That is, again, I mean, that the light ray propagates. You have reflection, refraction, and all sort of things. That there is a part of our school book curriculum up to 12th standard in science streams. But as we go towards the graduate level or so, then we start studying quantum mechanics, and we have the quantum theory of radiation that is, even taught in the advanced courses. So, right. But the things have come to the forefront when we talk about the computers. So the computers usually use these chips, and the signals that transmit for doing computations are carried over by the electrons, as you heard in the previous uh, session by Dr. Dhriti Ghosh, and that how the Fermi energy is there, and how the band gap is bridged, and how that basically tells you that the electrons filled up in the Fermi energy levels that actually are used. Sometimes they become conduction electrons to carry electricity, and that is the mainstay of all the computing that we have. So the whole idea of progress in building computers has been basically devoted to trying to squeeze circuits, and making your chips smaller and smaller in size. So you remember the computers that we had in 90s, and the smallest chips that are fitted in even in newer smartphones, not just laptops, that has become so small. But then there is a limitation, right? So the progress has been staggering. I mean, the Moore's law in computation that we know, that our computational power has increased multifold. So the Pentium processors, the very early ones that we used to have in 90s, I guess, they were really very weak, and now your mobile phones have, I think, better processors than them. However, there is a limit to this, the how fast you can make these chips, because the smaller the chip becomes, then at one point, the quantum tunneling effect, the leakages start to happen, and you can't really have this linear growth in computing power by just simply making the chip smaller and smaller, as all these companies, NVIDIA, Intel, and they are trying to do, by the way. But then there is a big focus on actually just switching over from the electronic way of transferring signals to the using photons as the carrier of signals. So that is, the forefront area of photonics. So it can really transmit signals and build a chip that uses maybe waveguides or some lines back and forth, and then design a circuit like that to do the computations. So that is a really forefront. So beginning from the ancient times, we were fascinated about light. Then that led to the systematic development of a theory of light that we call optics at the beginning, initially by old people like Euclid, Ptolemy. But today we are, after developing quantum mechanics, we are at a stage now that photonics is the forefront leading area where the new technology like trying to build computing power on the basis of photons, that is the one mainstay. So in all of this, if I have to say one principal aspect basically, that that uh, one principal the transition point, that is the development of quantum mechanics. And that it was developed around 1920s or so. That has led to the development of quantum theory of radiation, and now that has made this realization possible where we can go to these fast computers and maybe think about quantum computers later on. Okay, right. So this quantum mechanics, so we have all read it, some of us in very advanced form, some of us have taught it at various levels, and we all heard about Einstein, who was one of the key figures in all this development of quantum mechanics. So that is one thing. So that I am not even writing in this list, in fact, that where he has contributed through various means. But then we know him. He's famous for his theory of relativity, special relativity, as well as the special relativity then generalized to the general relativity, where you talk about the space and time then muddled with the masses, and then how the masses curve the space time. So that is the general theory of relativity. So he's very famous for that, and he's also very, very famous for photoelectric effect, for which he got the Nobel Prize. So, and you may not know, but the work that is in the areas of stock market now and related to earthquakes, that basically uses concepts from the non-equilibrium statistical mechanics, where stochastic random processes are need to be understood. And the basic equations for those stochastic processes were initially developed by Langevin, and but then Einstein also played a really crucial role in that development. He actually wrote down the Einstein-Chebyshev equations and really wrote fundamental papers on it. But I listed relativity, photoelectric effects, stochastic processes. But there is another topic that, as I am highlighting in this yellow, that is also very fundamental, and that is really important for the talk or the session that we are running on photonics. So I don't know, maybe if I ask you this question, so can anybody suggest like the way I am developing this session? So which topic which Einstein worked on or he put forward that I am thinking or trying to convey to you about? Like, can somebody take a guess and tell me? So which other, in this list, which other topic he worked on? So that will be the subject of this session anyway. So, but I just wanted to see if you can take a guess. Right, anyone?
Theory of light, optics.
Optics. Einstein, theory of light is
Theory of
absolutely
light.
to that, but Einstein optics is, we won't say that he had that contribution in optics. So what is, it is the exact thing we know that, yeah, and we all study and teach that. So that is really key in this. So okay. So okay.
Quantum mechanics.
Right, quantum mechanics, but again it's a big topic. So let's say we pinpoint like what exactly he did. So I already wrote photoelectric effect, but there is something else he wrote a paper on. Exact year is also there, 1917. He wrote a paper on that one. Okay, right. So it's on the emission, stimulated emission. Okay, so that we know. So we will come to that in a moment. So, and as I already said that the way I am developing this session, so I would keep it very linear, very pedagogical, and very simple. So I hope there is that you take home something new. I hopefully something new from this lecture today. Okay, let's move on. So Einstein did a lot of things, but the one about the spontaneous emission, stimulated emission, in particular stimulated emission, the intuition he had, that was really wonderful. That is central to this session today, and for photonics also, lasers. Okay, let's begin with some fascinating facts from astronomy. So there's a slight switch over here. So and it will be clear to you so why I talk about astronomy. So as we are talking about light, then what can be better than the sun? The main source of light on earth, we can build all sort of man-made sources of light, but the sun remains by far the most amazing and important source of light, not just on earth but for the entire solar system. And as in the universe also, the stars, the sun is one from the family of stars, and the stars are the main beacons or the sources of light in the entire universe. But sun is the source of light on earth. That's definitely, nobody can dispute that. Okay, that's the beauty of astronomy. So, like if you want to do an experiment in a material science or a physics lab, then usually you will have to, devise a lot of instruments you have to bring in, and you have to create your light sources and measurement techniques, this or that. You have to build a lot of things. But astronomy is such a cool subject that the nature has already done experiments for you. Where can you get a better source of light than sun? And not just the source of light, there's gas inside, nuclear reactions, the fluid dynamics, the hydrodynamics, all sort of fundamental physics that has been encaptured, and not just physics but chemistry is also encaptured inside just one astronomical object, any object you talk about. So the whole idea that the nature has done the experiments for you, you have to build some instruments to measure it or to observe the things. You just have to quantify, and then bingo, you have a really good way of doing science. So that's the beauty of astronomy. Okay, but then what we learn by looking at these objects, the fundamental things that we develop, they are not just applicable to astronomy, but they have a widespread application in all branches of science that we know. Okay, right. So, for example, the radar technology was in fact developed in astronomy, but in World War II, although for the it was used for wrong reasons, it just was used by the military to shoot down planes, and the use of radar technology. Even now, your traffic controller on airports, they are using it. So, right. So now I'll have another kind of a interactive question for you. So in front of you, you see a picture of the sun. So take a guess, like what do we call this sphere, or the disc shape that you see in front? And there are this some black dots also on it. So maybe some of you already know. So somebody wants to come in and tell what exactly you see, what we call this. Hello. Right. So this is the sun basically. So let me write it down. So the sun, and then it's called the photosphere of sun. So this is the central bright part of sun that we call photosphere. On it, you also see these black dots. Those are the sunspots. So uh, 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 so the dark points are sun spots. So just bear this in mind. There are a few observations you can straight away make, that the photosphere appears brighter in the center. This is through a filter, by the way, because you can't directly look into the sun. But it looks slightly, the faded or orangish, darkish color on the outskirts. So that's one observation. It's called limb darkening. That the limb or periphery of the sun, when we look through the filter, appears darkened. So that is purely due to the temperature effects, that the upper outskirts are actually slightly lower in temperature than the central bit that we are gazing through. But next thing is, I'll show you another picture of sun. So that was the first picture I showed you. Now look at this picture of sun. So now I have just, the blocked the photosphere, but I did not block it. In fact, this is from a solar eclipse that moon has blocked the, the photosphere. So, so what you see now on the edges, what do we call that? That is called the that is a different bit of sun that we do not see. If you go back, you see the round, the very clear edge of the circle that you see here, but that edge is now missing, and you see these flares and irregular structure around, because now the photosphere has been blocked, and photosphere is really bright. So it's something like when you're driving at night, and somebody from the other side of the road, if he's coming with his high beam on, then basically that blinds you. So the photosphere blinds us. It doesn't allow us to see the features on the surface of the sun. They appear dark to us. But if somehow the photosphere is blocked, as it is blocked in this eclipse, then what you see, the bright edge is called is the chromosphere. So I already gave you two parts of the sun that can see, but chromosphere is not visible during the normal viewing because the photosphere is so bright, it blinds us, even the light blinds. Okay. The next is, again you have sun, and it just so happens, the eclipses, when they occur, there may be some eclipse when the relative size of moon is quite big and it obscures both the photosphere and the chromosphere. So what do you see this in the light? So you may think that it is just basically the light, but actually there is this media prevailing around sun that is not visible in this image, that is not visible in this image, but it is actually visible in this one, that is called the uh, uh, corona of the sun. So that is basically high energy particles shooting off from the surface of the sun and getting illuminated, and that is what makes up the corona. It is a very hot region of the sun also. Yeah, but the surface is cold. Okay. So I wanted to give you these pictures just to give you an impression that look, even the light from the sun is blocking the components of the sun. So when the photosphere is visible, then it does not allow the corona and the chromosphere to be visible. They are only visible when the central bit of the sun is obscured, and then only you see the corona of the sun. Okay. Again, just for your, the clarity that all the three pictures are together. On the left, you have the photosphere, and then you have the chromosphere, and then you have the corona of the sun. Right. So, so what do we learn from this? That photosphere is this uniformly illuminated part of the sun, and the photons, just when they are produced at the center of the sun, they are just not reaching us directly. In fact, when we see photosphere, these photons were emitted 30,000 years ago. But now you would be confused. You know that the photons, they leave the surface of the sun, they reach us in 8 minutes, I think, if I am right. But what is this 30,000 years? So 30,000 years is basically the sun has a size, right? The photons are produced in the center of the sun, and then they do this zigzag random motion, keep bouncing back and forth inside the volume of the sun. Basically, the sun is so dense, it does not allow the photons to come out. So they interact with the atoms there, absorption, emission, these processes occur repeatedly, and actually scattering occurs. Uh, and then at some point, roughly after 30,000 years, after that they shoot us. So the photons do a random walks inside. So let me write it clear. Do random walk, and then they shoot off. Then they come to us. So this random walk takes 30,000 years. So the photons that reach on us, they were produced in the sun that back. Now after they leave the surface, then there is no more material, and that is straight come to us very fast at the speed of light. But initially, when they are inside the sun, they are not allowed to leave. The sun doesn't allow them to leave. In fact, from the very massive stars, if you do calculations, you will know that photons even haven't reached us. They take an entire lifetime to actually reach us, in lifetime of the star. Okay, let's move on. So then next, so after telling you this bit about the sun, now let me tell you about, like, sun is one thing by looking through the filters and or through the naked eyes, and you would see these pictures. But then if you look through the prism or a grating, then what you find is, you know, the one uh, one big bucket of light you get, you just pass it through the prism, and then you can break it into basically different wavelengths or the entire spectrum. So this you will all identify with the spectrum that we know. So, but again, the colors have been used and it is the visible part, but then there is a spectrum that extends all the way to, you know, after red to infrared and the regime, and on the other side from violet to then X-rays, ultraviolet, that region. So towards UV and towards IR this side. But the whole idea I want to tell you that the all the photons you get, you pass it through them prism, and then you break it into pieces and you get the entire spectrum. So you have the sun basically, you put a prism, the other side you get is what you see in front of you. But then again, you can count the photons also. You just not just that you find which photons you got, but you can also do another thing, like how many photons of what particular frequency did you get. So that basically then this is consider this color to be the x-axis, and then make a y-axis that is roughly that roughly places how many photons of red I got, how many photons of green I got. Let's say I put points on this plot, how many points of this wavelength, and how many points I got. Maybe I got 100 of this wavelength, maybe I got 50 of this wavelength and 30 of this wavelength. So I got roughly these many photons, and then I keep on counting, and then I count how many photons of the blue one and after blue of the UV one I got, and I will find that I got a very tiny amount, maybe few 10, about 10 photons of UV or so. So I keep on building this curve for each spectrum that I have gotten, and then I will find that, okay, this x-axis is the frequency and the y-axis is my number of photons or flux, you can put. So, and then I make the full plot, and then I get really this you know, nice curve that that we get. Just the spectra we got from the sun or from any hot body. So, and we call this spectrum, if somebody has a say on this, then what we call, we get a black body spectrum. If we count the photons of after passing through prism, if we count the photons of what type of photons we get. Now, not only that, the spectrum can be continuous, as you see this upper, you know, the strip which is very continuous, but then sometimes you have seen these pictures where the entire strip appears dark and you only see some lines in the spectrum. So in the plot that I have made down there, then it will not be a smooth line like this, but the plot will look like this, and then wherever there is this emission line like this, wherever there is this emission line like this or like this. So this is called the emission spectra. And on top you have the black body spectra, and then the absorption spectra basically that is there. That is basically, now you see the entire strip like the whole yellow curve, but somewhere the curve is cracked. So let's say at this point where there is a dark line, there is an absorption feature. So this yellow curve is kind of, you know, bends here and gives you a dip here wherever there is a feature. So here is a feature, so it will be a dip here. So that we call a continuous spectra, but with absorption. So we call this absorption spectra, that some of the photons of a particular frequency are missing from the spectra. Okay, so this is the spectra we get from sun also. In fact, if I were to show you, so it's exactly this. So, and you know, the black line is theoretically predicted spectra of a black body that is at 5250. So it appears as you know, all of a sudden to you, but that's what we will be developing slowly, like where the theoretical line come from. But yellow is the actually observed spectra, and look at the rough or approximate match that you have between the black body and the spectra you get from the sun. But then there are again some missing, there are these missing cracks that appear in this. So you see there's a white crack down at multiple locations. So I think I should go slowly on this one. So there are two colors you see. One is a color red, that is basically the spectra that you receive at the surface of Earth. But at the surface of Earth, the spectra from Sun has already passed through the atmosphere of Earth, and in the atmosphere of the Earth there is oxygen, there are water vapors. They eat through the photons of the Sun, and the spectra is very depleted. That's why the red spectra lies below, and it has these big chunks that are missing from the red spectra. So that is basically the depleted spectra at sea level or at our location that we get. But the yellow is when you measure the spectra from the space station or from the top of the atmosphere, then it is not depleted because it is straight away coming from the surface of the sun, and in between there is more or less vacuum. But then still there are some tiny absorption features. It is still not like the solid curve that we expect. There are some features. There are some that we call the dark lines, although they appear like these white cracks in there where the photons are missing. So that is the top of the atmosphere. That's the point I wanted to make. This appear because in the uh, outskirts of the sun, on the surface of the sun, there is this cooler gas, these hot photons, the perfect black body photons that are coming from the center of the sun after multiple scattering. When they pass through this cooler gas on the surface of the sun, and then they give rise to these absorption features. Okay, that's why the yellow spectra that is observed is not exactly like the theoretically expected the black body spectra, but it's still the comparison allows us to estimate the temperature of the sun. Okay, so elaborating on this same point, so inside the sun, the continuous spectra is present. Is it present? Not really. Because in the process of nuclear fusion, only specific wavelengths are emitted. But when those wavelengths, they do the random walk inside sun, so they keep on doing this zigzag motion. So they, at each scattering event, they exchange energy exchange occurs, and the photons they are re-emitted, and their energies get redistributed. So you think it of as a black body cavity that is created inside the sun, in which the photons are bouncing back and forth against the scattering centers, and their energies get redistributed. So initially, to begin with, maybe there is one particular type of photons that were emitted in the nuclear reaction process, fusion process, but then their energies get redistributed, and the end product is a very continuous black body type of spectrum that is created. So I will draw this here, that redistribution leads to this continuous spectra inside the sun. However, the outside of the sun is, as I already told you, it is the gas that is cooler in nature, that is not so hot. It's a cool gas, and then that gas actually, when the full spectrum is coming out after this, the creation of this black body spectrum after multiple zigzag random motions of photons, this is created. But when this comes out and passes through the cooler gas on the surface of the sun, that gives rise to these dark lines, the absorption lines. You see the dark lines that have been created. Now, interestingly enough, I must tell you one more thing. Where the dark lines appear, if you were to point your device and mask the lower portion, and you point your observing device, let's say I call this your observing device, on this line of sight on the top part of the sun, where you know that from behind no continuous spectrum is coming, you are only looking at the top bit, and then what you will find is that corresponding to the dark lines that you see when you look straight, there will be similarly only emission lines that are coming. So it's like when there is no source sitting behind, then from the upper part of the sun, you get uh, uh, the emission line spectra, but corresponding to the same wavelengths at which we observe the dark lines in the spectra when we look towards the center of the sun. So interesting dichotomy. So, and then the key behind this phenomena is what we know as the Kirchhoff law. So you would have heard Kirchhoff's name in the your electronics books and topic. And then But this is the Kirchhoff's law of radiation. Basically, when there is a hot source you are placing behind, and then there is a cloud of gas in front, then the light from the hot source, when it passes through the cloud of gas, and if the gas is not very dilute or not so dense, then in that case, the gas would result into the depletion of these photons from the continuous spectra, the black body spectra emitted by the hot source. So those depletions, so they are causing these dark lines or the absorption spectra, as you see. After the the black body curve comes from the left, it passes through, gives the absorption spectra. Uh, but the actual spectra is a continuous spectra. Or if I were to count the green photons, blue photons, I have already described to you, and make a plot of a number of photons or flux on the or luminosity on the y-axis and the frequency of the photon on x-axis, I will get a curve like this. That is basically the same. It's continuous spectrum is a black body spectrum. You will get from a hot object. Now, the gas itself may emit depending on its temperature, and then you will get the emission spectra. So that's something happening when you point your detector towards the upper bits of the sun, where there is not the hot body of the sun is not sitting behind. You're just looking off the top or bottom portion of the disk of the sun. Then you will get the emission spectra. Now, this is not exactly the Kirchhoff law. This is in the direction of the Kirchhoff law. What Kirchhoff told us, it all depends on this gas cloud. So what do you mean by this? So you mean is that if the gas cloud is sufficiently dense, if this is sufficiently dense, so I can write this statement here, then, and maintained at a temperature, and it is sufficiently dense, then what will happen? That it is so dense that this absorption spectra is like there is no spectra. Everything becomes dark. Now some photons are missing, but it was coming from behind that passes through, that filters through, and you get some photons that are missing because the gas cloud is dilute. So, but if it is not dilute, but it is very dense, in that case, all the photons will be taken up by this spectra, by this gas, and then what will be then this so absorption spectrum completely dark if the cloud is dense. But then that cloud, it will take all the radiation, the photon that is coming from the hot source, it will bounce back and forth inside this cloud, and it won't be allowed to go because it is just doing this back and forth bouncing thing. And its energy will be redistributed, and again that energy will appear at another black body curve. So emission spectra will not be an emission spectra, but actually if it is dense, so if dense, then the spectra you will get is a black body spectra again that will be emitted by the cloud. So the absorption spectra will die completely, everything will become dark, and that the gas cloud, the dense gas cloud, will start emitting a black body spectra. It is as if the gas cloud, after taking that radiation from behind, it has become another source of a continuous black body spectrum. That is the Kirchhoff's law that he put forward, that the gas cloud will start behaving as a black body. So now it's kind of a very fundamental understanding about what are the black bodies. Black bodies are not really, you don't think in terms of some sources or some hard bodies, this or that, or we thought sun is a black body. Anything can be a black body, just that you have to maintain it at a temperature, and inside the material should be so dense that any photons that you send in, those photons, they bounce back and forth enough times, redistribute their energy, and then that cloud or that body in which this bouncing back and forth is happening, that becomes a source of continuous spectrum of light, and that spectrum is a universal shape spectrum that we call the black body spectrum. So right, so in a more illustrative way, cleaner way, so you have a hot source, and then there is a cloud of gas that is sitting. The hot source was emitting a continuous spectrum. If the cloud of gas is thin, dilute, the optically thin and dilute. So optically thin means that light is allowed to pass, then dark lines will appear, and then on the bottom the bright spectrum appears, that is the emission spectrum. However, if the density of gas is higher in this gas cloud, nothing will pass through. The continuous spectrum with dark lines that we call the absorption spectrum, that dies, that will not be there if the cloud is dense, and only emission spectrum will be coming, and it will be exactly the same. So if the cloud is dense, right? So I think already explained that. And again, I mean, why I am showing that this cloud emits these different and where the spectra comes from, the way is a very illustrative diagram that that you have to pass through prism, and then you can break the spectra into just to see exactly what sort of spectra you are getting. Then you can do a further photon counting, and then you can plot it on x and y axis, then you get the curve for continuous spectrum, that is the black body curve. For the emission spectra, you get a curve where you get only lines, basically. Some points in between there is zero frequency. So at any point, please, if you have any doubt or if you want to say something, then you are always welcome to come in and say something. Okay? Right, let's continue. So let's try to describe all this what I told you with the help of equations. So I told you that if there is a source of light, if I have a source of light, let's say a source of light that is emitting light like this, and if I place a cloud of gas in front of it, and then this cloud is depending on what is the density in the cloud, the radiation from the source, let's say I call that radiation I nu, enters the source, it passes through that source, maybe comes out on the other side. So I call this I nu, let's say I nu 0, and let's say size of my cloud is roughly say s, and then can be a variable size, the cloud is bigger than the s changes. On the other side, I get I nu after crossing through s. So that is the intensity I get on the other side. So right, and then as I already told you, two things can happen: the emission can happen, the absorption can happen. So I just have to write an energy balance equation that intensity I nu can change by 1 emission, by 2 absorption. And as you know, intensity goes in, some atom inside absorbs it, re-emits it. So when it emits it, that is emission, and that will add to the intensity available to us. And if it absorbs it, that will deplete the intensity. So basically, I can write down an equation where rate of change of intensity per unit path length, di nu by ds, it depends on J nu, that is the emission, and that is a positive bit. It adds to the, at each successive step inside this length s, it adds to the thing. And then I can write another alpha nu, that is the absorption coefficient, but it has to be multiplied with I nu, because if there is no radiation coming from behind, if there is no I nu, then there should not be any alpha nu, or should not be any contribution due to alpha nu, simply because there is no radiation coming, then how the radiation can be absorbed. So it has to depend on how many photons are coming. So I have to multiply with this I nu here. So that's how the dimensionality was also fixed. So this is called the absorption coefficient. So I could write a very simple equation. Similar equations you study in many branches of physics. This is simple, the path differential rate of change of intensity of light in your, when it is passing through. So this is your source basically. When it is passing through a cloud of gas, and I already described to you, that when the cloud is very dense, then so many times the photons will bounce back and forth that out it comes is a black body spectrum. Again, the cloud will start behaving as a black body, and then it will re-emit, whatever the light was coming from it, it will re-emit at it. Now there is another point, the black bodies have a corresponding temperature. So a dense cloud, if the source was at a temperature of say 5000 Kelvin, and you send it through a gas cloud that is very dense, but it is only at a temperature of 100 Kelvin. So initially there will be a black body that is coming from the source, that is black body of a 5000 Kelvin, that is entering the cloud. Then those photons are redistributed, and on the other side you get a black body that is corresponding to the temperature of the cloud, that is about of the 100 Kelvin. Now you would say, how is the energy balance? The energy balance occurs because the cloud in the process is Again, in equilibrium with the radiation, it's heated up. So, right, now coming back to my equation that I just wrote, it is the transfer equation. It is the fundamental equation that is used in laser in every branch related to radiation. So let's write it again. It's a very simple differential equation. You all will be able to follow what I am doing. Just pay attention, and I hope I am able to ignite your curiosities up to this point. So this is the equation. So I want to solve this equation. So for solving this equation, let's say I want to write a general solution of this. So let's do a simple trickery mathematics here. So I think it won't take much time. So what I will do is, I will write, take alpha nu here and then define J nu over alpha nu minus I nu. Just follow in case I miss, small, if I make any small mistake in this one, just remind me so that I also know that. Uh, so next is I nu, and on the other side is just alpha nu, and I send the ds there. So I do this, and I simply integrate it now, assuming for the time being that I'm not really thinking that J nu and alpha nu's are something, depending on the integral. So I just say that they are just there, J nu over alpha nu. In fact, let's do a thing. I call this, both emission coefficient and absorption coefficient, they are the properties of the cloud. So I call them S nu, let's say. This is the properties of my cloud. So, and on this side, I have then alpha nu ds. Nothing I have done. I just rewrote this equation. Now I just want to integrate it. This is a very simple integral. So let's say we do it. So we get as nu minus I nu. There will be a minus 1 because there is a minus there. And okay, so I have minus alpha nu ds. So plus there is a constant c. So I fix the c like this. I say that uh, S nu is the property of the cloud, so that is not there. Initially, at S is equal to 0, so if I go back to my diagram, initially the radiation that enters the cloud is I nu at 0 length, that is I nu 0. So I call that at S is equal to 0, um, I nu is I nu 0. Okay, so I do that. So log nu minus I nu 0. That's how. So I'm not missing any step here because don't want to. So then, and you get minus alpha nu ds. Oh, this will become plus because there was a minus sign down there. So plus c. So that gives me the c. So c, I put in the value of c, and you can just try for yourself as you put this value. Oh, sorry. So this will be 0 because if there is no s and you are integrating over s, and at the beginning there is no part you have covered, so this quantity is 0 anyway. So uh, so you will get s nu minus I nu 0. So I brought that the log of the constant side, and in the equation I will get alpha nu ds. So I will again, let's say, define this quantity on the right hand side as tau. That is actually called tau, the optical depth. That's basically the absorption coefficient integrated over the path length. That is your optical depth. So now, so the next bit is basically you can write this solution here. So take an exponential, and then after a little bit of mathematics, you will arrive that for any general path S, so your I nu is I nu 0 e to the power minus tau, and then plus the S nu 1 minus e to the power tau. Okay, so in this equation, you can straight away see that if the tau is 0, which means that cloud is optically thin. That is one thing, or one way of saying it. Or other way is that the radiation is just coming straight to you without passing through anything. So dilute cloud, low density cloud, or basically optically thin we call it, then in that case your I nu would simply be, tau is equal to 0. That means the e to the power minus tau is 1. The term with this one that vanishes, and then only this term remains, and you get I nu 0. So that basically verifies that you get back the radiation that you have sent in if the cloud is dilute. So you may get some correction. So for tiny tau, for small tau, we can use tau e to the power minus tau as 1 minus tau, and then you get I nu simply as I nu 0, and okay, minus tau here plus S nu 1 minus 1 plus tau. So that basically gives you uh, S nu and minus I nu 0 tau. So okay, so that basically gives you the optically thin regime. So this way you can construct that the radiative transfer equation. So it gives you back the same intensity if you were to if you were to just have no cloud sitting in between, or a very optically thin cloud, or in a slightly, if the cloud has a small density, then in that case you will get a depleted spectrum with the tau multiplied on front. That is the spectrum you will get is of the emission line. So in all this process, what is S nu? So it was a ratio of the emission coefficient and the absorption coefficient. So it is the property of the system. So it is the property of the cloud. So if the cloud is of sufficiently high density, then if the cloud is of sufficiently high density, then the cloud will start re-emitting. So gives S nu is a black body spectrum. So that we already discussed in the Kirchhoff law. And I already described the relevant mathematics to get the absorption lines or the S nu or these bit. That for that you basically get it. So let me tell you that Kirchhoff law bit also. So going back to the solution. So this is our solution. So what is a very dense cloud? So a dense cloud means that okay. So this solution. Let's come back to this solution for a dense cloud. So the solution that we had is I nu e to the power minus tau plus S nu 1 minus e to the power minus tau, after solving that radiative transfer equation that I wrote in the beginning. So that for dense cloud, tau is very high. So tau is what? It basically absorption coefficient multiplied with the path length, integrated over the path length. Tau is very high. Say tau is like approaching infinity. So that way we can take the limiting case. So tau high, solution will be first term vanishes. So this is your incident, basically incident radiation, plus the second term gives you S nu 1 minus then 0 again. So what you get back is S nu. Okay, so that is basically the black body spectrum emitted at the ratio of J nu to alpha nu, which is a property of the cloud. So I have been saying up to the point that you will get back S nu, but in the equations I only wrote that S nu is nothing but it is a ratio of J nu and alpha nu, and it is the property of the cloud. But you will get back the black body radiation as Kirchhoff observed. We saw that. So in the sun also something similar happens. The photons in the nuclear fusion are emitted at a certain I nu 0, let's say in the center of the sun, but then inside the sun they keep bouncing back and forth, and then finally equilibrate with the radiation, and then S nu black body spectrum is there inside. But when that black body spectrum passes through the surface of the sun, then there is a depletion in that. Okay. Now, pay careful attention here that if this tau quantity, somehow if this tau quantity is, right now we are putting it a positive, and then e to the power minus tau is there. But imagine if tau is negative, and then e to the power even tau becoming 100 minus 100, then e to the power 100 is about 10 to power 43. So that means any incident small radiation you will put I nu 0, and if you multiply with a negative tau e to the power 100, then you will get back I nu that is 10 to power 43 times the one. That doesn't happen in case of sun. It does happen in case of, we know all in photonics, in case of the laser principle. Somehow you have to have a negative tau so that the amplification can be achieved of the incident I nu 0 signal. Okay, so we will coming to that in a moment. Okay, so what exactly is the black body function and how does it emerge? So we'll have to look closely when what goes on inside the gas cloud, the Kirchhoff's law. So, so I told you that a gas cloud, a radiation source, when it's shined on the gas cloud that passes through the clouds is sufficiently high density, then you get a black body spectrum out of the gas cloud. But uh, uh, but why do you get the black body spectrum? So this is something about the sun. We thought we can do this experiment in lab also, where we, let's say we have a gas in some container and we place it in front of a light source, let's say sodium doublet line, and then that is passing through. If the other side, if you can somehow, or maybe shine a very bright source from behind, and if the cloud absorbs all of it and then re-emits on the other side, and the cloud is of sufficiently high density, at the other side you will get a black body curve only. That we also call the Planck black body curve, or that comes from the Planck's law. So people were thinking about this problem, and then like how do we actually try to understand it? Simply by looking at the gas cloud, simply that a gas cloud, the S nu function in my radiative transfer equation, that is a ratio of J nu and alpha nu. Why do I get a black body? If dense. Why do I get this curve for the ratio of these two quantities after the radiative transfer equation? In the real life we see it, and in here we see just the S nu, we don't really see whether the S nu is something or not. And then Einstein asked this to himself, that what leads to this Planck's black body law? But Kirchhoff is also finding Kirchhoff's law is also, I can add, because Kirchhoff's was purely phenomenological. He just saw that the cloud are emitting these black body curves, and Planck also gave an explanation of the black body. I think it was later though. So, but the whole idea was that you shine a light on a dense gas cloud, and the other side you don't get absorption or emission spectrum if the cloud is sufficiently high density, but rather you get a black body curve. So it is written here on this image in terms of lambda. I can write a corresponding expression in terms of nu, so it would look like this. So think it of as a simple function in pure mathematical sense. If we talk about it, is a nu cube sitting on the top, and then e to the power h nu by kt minus then 1 is sitting in the denominator. If a student or anybody is asked, like, let's plot this quantity, and when they will plot it, they will find that there is a curve like which rises up and then comes down, and the curve corresponds to the temperature that is there in this equation that will appear. That is called the black body. Any gas cloud that is sufficiently dense, maintained at high temperature, shine from behind, will emit this black body curve corresponding to this temperature. So, and we solved through the equations, and then mystery. Why black body curve? So then there comes the famous this paper that I was listing in the beginning, and I didn't really tell you that he discovered relativity, he discovered photoelectric effect, he worked on stochastic processes and many other things. But this is another really fundamental thing that he wrote. It's a German paper that is basically Zur Quantentheorie der Strahlung, basically means quantum theory of radiation. where you can already see in front, right? There are some these equations that you can see in your cube, so that where he is talking about this a very exact problem, like why there is a black body curve that comes out of the cloud if it is very hot, and so what goes on inside the cloud, what is really happening in the cloud. Okay, so I think I can, at this point, I can take a brief 2 minutes break, and then I will begin the Einstein's bit of the story, that is, the final section of this session today. So I'll take some questions. If you have any doubts at this stage, then please feel free to ask, or any clarification, or if you want to add something. And then I will begin why I begin from the explanation from inside the cloud, what goes on and how do you get the black body. So, any
Sir,
yeah?
sir, is not there any scattering from the gas cloud?
Yeah, so absolutely, you nailed the point. So the equations that I'm writing, these are purely considering emission and absorption. Scattering complicates the equations. It is there. It redistributes the energy as always. But I mean, at the end, you will come back at the same conclusions, but it will complicate the equation. So there is scattering. So I cannot deny it. Yeah. Uh, is that clear? Do I answer your question?
Yes, sir. Thank you, sir.
Okay. So yes, so just to repeat myself again, that there is emission, there is absorption, and then there is scattering also. So that basically then it's kind of, you can say, the next chapter from the book of radiative transfer, where you bring in the scattering also. It will complicate the equations, but the fundamental things that we are discussing in this session, they are not going to change with that. Any other doubt or point somebody wants to make? Okay, so I think then we should continue. So the whole point is that dense gas cloud, and about the black body spectrum, so it is a spectrum with the functional form something like nu cube proportional to, and you can, if you want to plot this function, so this is your black body function. Let's say I call this bu, and then if you I call it s nu actually, because otherwise I will be confusing you with my notation. So, and then that is what you get from the dense gas cloud. Nu as a function of your s nu, that rises, goes down. You can see this, the nu cube factor, it brings it to 0 on the origin, and then the other side there is a tail because of the denominator exponential. Okay. Right. So Einstein had this. He was perplexed by, okay, you get this black body curve, but can I really derive or get this black body curve out of just by some fundamental thing I can devise or introduce about the cloud itself, what goes on inside the cloud? So that's the paper, this 17 paper he wrote about. So he began like this. So I'll just complete the session with this. So he began like this. So he said that, okay, what goes on inside the cloud? We all know it. We have all studied it, probably not from this angle as I am telling you. So inside the cloud, there are, there are atoms, there are energy levels, and then let's say there is an energy level E1, there is another energy level E2. So, and then so there are two fundamental concepts he could think of. So let's begin it like this only. Okay, so the two fundamental concepts, like what, like there are the levels are populated, that the first is that if like corresponding to the temperature. So another thing is there, that uh, given a cloud, then you have to have like because because of thermodynamics and statistical mechanics that some of the levels will be populated and some will not. So the level population in general is determined by this. So if n is the number that of a certain you know level is occupied or not. So that depends on the the Boltzmann's the energy factor that e to power minus by e by kt. Okay, so that basically governs like which levels are populated or which are not. But okay, so we will come to that in a moment. So coming back to the two fundamental processes are spontaneous emission that can jump downwards and emit a photon, or there can be absorption. So uh, and absorption needs radiation. Again, we are talking about, we already talked about the emission coefficient and absorption before, but then you can have photon here incident from the side, and then uh, say some h nu. This is h nu emitted, that h nu is absorbed and it jumps up course on the upper energy level, E2. So the probability of transition, say from when jumping in the spontaneous emission from E2 to E1, say some A21, and then so we call this with probability A21, and then probability of the other way around, the jump from the ground to up, that for the absorption, that we call P12. So anything can be, so the stimulated, as you know, is not, I haven't put here, but absorption can also be thought as a stimulated absorption, because you need a photon to stimulate an absorption. Without photon, you can't have an absorption anyways. But anyway, so at the beginning, there was no stimulated emission for that sake. Only two things were there: spontaneous emission and the absorption. So that's where he began with. And the whole thing he said that if your system is in equilibrium, then the the total energies that have been exchanged on the side of the spontaneous emission and then on the absorption, they should be same. So, and he famously, as you study and teach in your courses, that wrote this. So for the spontaneous emission, you just have to have the how many the population in your levels, and then multiplied with the transition probability n to 1. So that will govern like what is the total of amount of energy exchange that is occurring. And on the other, you again do the same thing: probability of your transition, and the the lower level is n1 and the upper level is n2, the population. So then your n1 b12, but this is the absorption side, but this needs input radiation. So I call that input radiation, say okay, I use a different symbol now. So let's say u nu, I call that. This is the input radiation or the radiation available inside. So you know that. So then, okay. Now by this, he set out to write. Okay, if you have this, then I can get an expression for my u nu. Okay, so let's say what is my u. Okay, otherwise let's not confuse again. I will just put u, not u, so that we get out the same thing, the s nu thing. So this is basically the N2, the population levels in the second level, and then A21 is the transition probability from 2 to 1, that is the spontaneous emission. And then this is the absorption. And in equilibrium, both should be balanced. So that was the whole principle he put forward. So then by this, I should be able to derive what is my radiation field S nu. So let's try to do that. And he knew that the levels n2 over n1, their ratio is again governed by the Boltzmann population occupation expression. So that ratio of the energy gap, so that depends on the energy gap basically. It is this one, that corresponding to a certain temperature, then how many N2 will be there corresponding to N1. So this ratio is like that. So once he had the ratio, so then he could simply write his S nu, that was A21 over B12 e to the power h minus h nu over kt. Right. He was very happy. So with this, and he thought, okay, let's plot this expression. So in fact, by dimensional analysis, you can also get that the A21 and the B12, that is roughly proportional to nu to the power cube. So he was able to get up to this point, that he gets nu to the power cube power minus h nu over kt. And he plotted that, and he was expecting that he will get the black body curve, but you all know that what he got from this analysis. So that the tail he could reproduce, but not the full black body curve. So he thought, so Einstein thought there is something missing in his analysis. And at that point of time, because he could not recover the black body curve, at that point of time, he said that, oh, and that's the breakthrough intuition he had, that maybe there is a third thing, not just the spontaneous emission and absorption, but then there is another, basically that you have a photon coming from left, and then that induces the jump, and this is called the stimulated emission. And then apart from the spontaneous emission and absorption. So, and then there he, no, so just the jump, and that emits a photon, and then the absorption. Right. So, and then again, this is level E1, this is level E2. And then again, let's try to repeat the mathematics, what Einstein did in his paper. So, so now let's say we have the third process. So we write B21 for that. That is the transition probability. And then for the spontaneous emission A12, and then this is A2. Sorry, this no. So this is P21, and this is P12. So again, for stimulated emission, the radiation field is needed. For absorption, the radiation field is needed. But for spontaneous emission, it is not needed. The emission adds and absorption takes away. It's a negative feature, and emission adds is a positive feature. So I write my equation like this. So stimulated emission is B21. So I write a B21, but I need the source of radiation in this case as nu, let's say, and then B21, and then with the N2 to 1, it is jumping. So I multiply with the availability in N2, that is my population N2, and then plus I add the spontaneous emission, that is A21 multiplied with the N2. So these are all emission covered here, and then radiation field incident on B12 probability, that is for absorption, and then N1. Okay. So, and now I have to write out of this, I have to write an expression for S nu. That's what exactly what Einstein did in his paper. So let's not worry about this one here. So we can write that same expression here, in fact. So S nu B2 P1 B21 Okay, so this is the reverse way. So, but uh, forget it. So I just want to write my S nu from here. So S nu is A21 N2 divided by B21 N2 and B12 N1. And because the stimulated emission and this stimulated absorption, they are just the exact opposite process of each other. So the B21 is nothing but B12. Okay, so again, some of you might have noticed that I am missing the G factors that are there usually in these calculations. For the sake of brevity, let's say that there's no degeneracy, so I have just skipped the G factors for the time being. But so B21 is equal to B12. These are the just invert processes of each other, stimulated emission and stimulated absorption. So S nu you get is A21 over B12 divided by say okay, so 1 minus N1 do I did I do this correctly? So I hope I no, there's a reverse side. So this should have been plus, this should have been minus. So I'm sorry for that. So that means this is plus, this is minus. So what S nu he got? A21 divided by B12 and e to the power uh, no n1 over n2. So n1 by n2 minus 1. So we already wrote n2 over n level populations are minus h nu over kt. So reverse is plus h nu over kt. So s nu we get from here is okay. Uh, so this is what is a black body curve. So that way, he just by comparing, if he just takes into account spontaneous emission and absorption, and he doesn't get back the black body curve, but he only gets back the tail part, the e to the power minus h nu by kt, the genes part of the curve, let's say. But then later on, when he introduced the stimulated emission, as we can see, so with this simplistic of simplistic mathematics, that you can easily get to the S nu being a black body function. So that was his remarkable achievement in that sense, that he could uh, get out the concept of a stimulated emission. Uh, by using the concept of stimulated emission, he could prove that the cloud, it in fact should be emitting the the black body. So why these things are why we need these things and why we need to understand this, not just here but for all the quantum mechanics, and because the same principle is used in laser. So coming back to my transfer equation, so if you remember that one, so I knew was at any point that e to the power minus tau and then plus s nu e 1 minus e to the power minus tau. So this tau quantity is depends on the absorption coefficient alpha nu uh, ds, and your alpha nu is again it's basically the what is the total energy at any stage. It's basically you take the alpha nu I nu, then integrate it over your volume element, your frequency range, your solid angle, and then the time bit, and then what you will get is the total energy. And the same total energy exchange that you can derive is from the level population inversions that you have. Like, so we are talking about the alpha nu, the absorption bit. So in the Einstein's, that last bit I talked about there, how the absorption will happen is that you have to put uh, how many total n1 is there, and then what is the corresponding transition probability from 1 to 2, and then you have all the bits. So now multiplied with the volume element, the frequency, the steradian, and the solid angle, and then the time bit. And of course you have to take care of like each photon may come or go from any direction, so h nu over 4 pi. So comparing, this is again the dE in Einstein's thing, and this is the dE in our transfer. So this is in Einstein, let's say. This is in transfer. So comparing these two, you can easily see that alpha nu would be nothing but it is n1 a12 and h nu over 4 pi. So this is your alpha nu. So now not only that, you know, the stimulated emission is kind of a negative absorption. So I will have to write oh sorry, there is no a but b factor, so my bad for this one, and then n1 here, and then similarly the total alpha nu that we can write for both the stimulated absorption and emission. So that will be B12 h nu over kt minus n2. So that is the jump from up to down. The level of n2 will matter in this one. That is from h nu over kt. So your alpha nu would be n1 minus N2, B12 and B21 are similar, so I don't have to repeat them. And then this is it. So you can write, take N1 out, and then N2 minus N1, that ratio is h nu over kt, B12 h nu over kt. So if your you know the alpha nu quantity, so what we have used here, so I will write it again, alpha nu n1 1 minus n2 over n1, and for that we have used the uh, population ratio of the levels n2 and n1. There were two levels, and then the ratio is minus h nu over kt. In case of laser action, so in case of normal procedure, n2 is always going to be smaller than n1. That in that case, the quantity n2 over n1 will be small and alpha nu will be positive. So in normal situation, so usually alpha is positive. But in case of lasers, the population inversion that we achieve, where N2 level is higher in population than N1, then in that case, the term in the parenthesis in the bracket, N2 over N1 is different in that case, and alpha is higher in that case, and then it is much more than 1, and then alpha nu is negative. So in case of population inversion, N2 over N1 is greater than 1, and then alpha nu is negative, and your tau optical depth, that is basically that is alpha nu and a path length. Let's say tau achieves is minus 100, then the intensity multiplies by e to the power minus tau, and that can be of the order of 10 to the power 43, for example. So that is what we call the laser amplification, and that is all the basis of the lasers and that in the photonic devices that we build, that we use for the building the lasers. I think I was a bit rushing, so maybe we can go through this as you asked me. So I think I wouldn't be saying much more on this topic, and I leave you with this picture of the laser technology and this methanol measure that has been observed recently by Arecibo Observatory from the astronomy around a star. That's a naturally occurring laser, you can say. It's also measured in the microwave frequencies. But the whole concept and whole principle, it impinges on the concept of stimulated emission by Einstein, and I hope I was able to explain it to you. So it's open for discussion, so anybody can come in, and if you want to ask or say something, please do. Hello?
Yes, sir. Sir, you have explained actually very well way. and with equation and each and every equation you have explained the phenomena, what it is explained. I think I have no questions.
Okay, thank you.
Thank you.
Okay. So in between you may have questions, but I would like to like if some of you can want to open up your videos and say a few things about like how do you like the whole experience about our sessions and talks about about the FDP in general. So that's like a feedback from your side. So you feel free to, I mean, one by one, if somebody wants to say something. Yeah. Okay. Anyone have a question, or if you want to add, we have about 10 more minutes, and then we will break for lunch. Next session will be at 2:30. Uh, Very faint. Can you speak a bit louder? Hello.
Session is very much interactive as well as yesterday light journey, and there are certain sessions where they are like research interactive talks, where in which they are instigating the research component in us. Truly a great help to all the scholars, sir, and I thank you for the opportunity.
Thank you very much.
Thank you.
Yeah. Okay. I think then if no more doubts or discussions. If anybody wants to come in, then maybe one last time, and then we will break for lunch, and then we will be back with the talk by Dr. Sudhanva Patra at 2:30.
May
So
I ask one question, sir?
yeah, sure, go ahead.
Uh,
And
Sir,
also, if you can switch on your video for once, if possible.
okay, okay. Sir, I wanted to know what are the evidence to support that photon inside the sun travels on the zigzag path. Is there any evidence, some model, theory, or experimental results on which you can claim that the photons travels on the zigzag path in the sun?
Okay, so you know the photon has to be emitted somewhere. So, for example, if let's say if you guess where is the photon emitted, so let's say take a guess. So the photon is emitted in the nuclear fusion process, right? When the hydrogen nuclei coalesce to form helium. So we know exactly by that nuclear reaction that what photon is emitted, at what frequency it is emitted. So in principle, if that frequency and that photon is emitted, then we should get that. But when we put our prism and measure the spectrum, we do not get that photon. So we are really surprised. Oh, we know that hydrogen is fusing to helium. We know the reaction. We know what photon is emitted, but we don't get that photon. So there must have happened, something must have happened. It definitely nothing happens between the surface of the sun and earth. That is all vacuum, almost vacuum. Photon state comes to us. So something must have happened to that photon inside the sun. and that's how we build backward. And then we try to see, oh, okay, is there something similar happening on Earth also? Then we try to see device experiment, look in the clouds, and then we know repeatedly that any high energy radiation that is coming, that has a smaller cross section, that is quickly absorbed inside our bodies. That's how it causes cancer and other things. So high energy radiation that does that. X-rays, they do that because the matter, normal matter, it absorbs it, but after that it is degraded. So something similar happens in the sun because it is encountering these photons, high energy photons. It is those photons are encountering these atoms and the dense gas inside the sun. So they are absorbed, scattered, re-emitted, and they are not allowed to leave. Every time they change the direction, the density is so high. So that's how we know.
Okay, sir. Thank you very much, sir.
Yeah, other thing, a very simple analogy I can give you. Think of a forest, and let's say you are driving a truck or maybe a jeep inside the forest, right? So you can do two things: count the number of trees that are there in 1 acre, and then check the size of your vehicle, like a car or whatever you are driving, and then see, okay, my vehicle size is this. Their 1 acre of land has 1,000 trees. So what is the rough number density of trees in a small patch? And then you will know that whether the jeep will be passing straight through the trees or it will be colliding with the trees. So that is another calculation that can be used. So we know how many trees, in a sense, atoms are sitting in the sun given the density of the sun, and then we know the size of our photon, let's say, if it is allowed to pass or not near the vicinity, the impact parameter basically, and that tells us that, oh, it is not allowed to pass. The density is so high that it will definitely be bouncing back and forth repeatedly.
Okay, sir. Okay. Thank you, sir.
Yeah.